So the other one is easy as well. Def method compose with their perm group G, which is a perm group, and then two elements A and B, which I could specialize on. I could specialize those on permutations, but I'm not going to. I probably should, but I'm not going to. It might be useful to specialize on different things when we create group homomorphisms and so on. So this is just perm compose A. So now if we do quick load CL permutation examples, if I do perm examples, make Rubik 3x3, so this is the cube group, the group that represents the Rubik's Cube. Then let's see, depth parameter. Let's make sure it works. Group order cube. Okay, good. We should be able to do identity element of the cube, and then we can compose two random elements. So random, what is it? Group element of cube with another random group element. If we compose this, and let's do 2 cycles, just to see what the cycle representation is. And that looks like it works. All right. So now that we have our protocol, so the reason I made our protocol is because I plan on next implementing another type of group, which is called a free group. So first let me commit this stuff. I'll probably rename it later. Let's take this out and get status. I hope I don't have anything else here. I have a few dumb things. Let's see. Okay, good. Git add CL permutation.asd source permutation group .lisp and source group.lisp. Git commit -m. All right. I didn't check the 43 quintillion number like I did last time. I know every Rubik's Cuber knows that if it starts with 43 and it has what looks like enough zeros, then it must be the actual order of the cube. So, free groups. Let's start on that file. What is git add -u? I don't know what that does. And I don't want to read the man page yet, but maybe you can tell me what it does. Oh, that's nice. That seems like a useful tool, but it seems dangerous too. That if you accidentally add everything you're not thinking, then and you don't check yourself, that you're gonna mess it up. So source free group. I will define what this is. Did I do this in the group file? Yes, okay. All right. So a free group is a group that basically the way I see it is it's a group that contains a set of symbols. So let's say the symbols are A, B, and C. And the group operation is essentially concatenation. So our times operation equals concatenation. Now, our group set can't just be ABC. We can't say G equals ABC, because that's not really, that can't work. There was actually one group law that I just remembered that I didn't say. Here, I forgot to say that elements have an inverse. Elements have an inverse, which actually means I forgot a protocol as well. Def generic inverse G compute the inverse of A of A. Okay, so I completely stupidly missed a big thing. The inverse of an element, if you know A -1 is the inverse of A, then we have the following property that A to the power of -1. I'm actually just going to say A prime. If A prime is an inverse, then A prime times A equals our identity element, which equals A times A prime. Basically, it's just like an annihilator. And again, with integers, the inverse of an integer is just its negative if our operation is addition. So big thing I left out. Fortunately, we can modify our last commit. But we should also go back into our permutation group.lisp, and we should add inverse. So inverse G perm group, and we have an element A. The inverse is just perm inverse of A. Okay. Let me patch up myself real quick. Git status. Git if. I do not want to add everything here. Git status. So git add source group dot list and source permutation group dot list. Git commit -m. I'm just actually just going to give it a random thing. Editor equals Emacs git rebase -I. Oh, git stash. Let's use this little thing. Let's do a fix up here. And let's see. So git log. All right, that looks good. So git stash. All right. So, okay, so rewinding a little bit. We have these three operations now. Every element has an inverse. You can compose two elements, and we can get the identity element. So going back here, where I caught my mistake, we can't just have a group that just contains these symbols. If the only things that we can make in our group are these symbols, then it can't be a group, because these symbols, barring any relationship that I haven't specified, you can't invert any elements. There's no element in this set that can invert A, for example. There's no thing that we can do to give us back an identity element. Second of all, we don't even have an identity element. So I'm going to specify there's something called 0 as the identity element. So really a free group is defined by a set of symbols, but we have to add some extra elements, namely an identity element, but also their inverses. I'm going to use that prime notation, B prime and C prime. So this is a perfectly valid set that we can use for a group. The only relationships that we need to specify is that these satisfy the group laws, namely 0 times A equals, or A times 0 equals 0 times A, which equals 0. That's one thing. Same with B and C. And the other thing is if we have some element X times X prime, that equals our identity element as well. So programmatically, we can generate all of these things. We specify the symbols that we want to use, and we can programmatically generate the rest. I'm actually not keen on even defining the symbols. While it's useful and maybe nice to provide strings as a mapping, we can just use integers to represent this. So this free group right here would just be represented by 0 as the identity element, 1, 2, 3, and then we can represent the inverted elements by their negation. However, it is super, super, super important to understand that this is not the this is not a group over the integers with some operation like plus or multiplication. Even though it looks like this is the additive group because zeros are additive identity, 1, 2, 3 are just elements, and then -1, -2, -3 are additive inverses. The free group sort of specifies that concatenation, like I said down here, is the main operation. So, so if we do, for example, 1, or let's do 2 times 3, the result is going to be something that looks like 2, 3. If we do, let's say x equals this, and I do x times -1, then we get 2, 3, -1. It is really truly concatenation and not addition or anything like that. So with that said, we can just specify a free group by the number of symbols it contains. So I'm going to define this as a class, and later on I might actually change the permutation group itself to be a class. But classes, the person that got me into the habit of learning to use classes instead of structures, when possible, is actually Shannon Spires. I worked with him at one of my last jobs, and he's a fantastic Lisper. And classes aren't really that much more expensive, and especially if we're not creating tons and tons and tons of instances of them, then we're not really getting penalized, and we get a lot more functionality. So, so we're going to def class free group, which doesn't inherit anything, and we specify the number of elements. I don't know if there's a proper term for this, maybe cardinality or something like that. I'll just say num elements. Accessor, reader would be num elements. Free group num elements. So yeah, free group that's a pretty simple representation. The real magic, quote unquote, is our representation of actual elements of the group. I see it as, it's a pretty simple thing. We should be able to, our elements are, like I said down here, the integers. So the representation of individual generators, I would say, are easy, but then we need to have somehow a representation of concatenation of these generators. So the way I think would be reasonable to do that is just represent it as a list of some sort. Maybe a list that is something like a queue, where you can maybe like a double-ended queue. A reader is just it's like a getter that doesn't have a setter. So if we want to find the number of elements in a free group, we just call free group num elements. So, so tentatively, I'm thinking that we can represent elements as, as lists, basically. A list is our concatenation. So elements are really, let's write this. An element is something that is either a generator G for a generator G, or